Hello and welcome back to my channel, and today we're continuing on from last video, and we were just about to start question 5 in the last video, and the question was, describe fully the transformation given by this matrix here. Now, the rotation around the z-axis, this looks very similar to that matrix. If you see a matrix with 4 squares that look a bit nasty, and then zeros elsewhere, and then one fixer, I like to call it, then it's going to be a rotation matrix. If the 1 is here, it's around the z. If the 1 is in the middle, it's around the y. And if the 1 is top left here, it's a rotation around the x-axis, because it fixes that axis. And so the one for the z-axis is cos theta minus sine theta 0 sine theta cos theta 0 1 0 0. So therefore we can equate, I'm going to do sine theta equating with root 3 over 2. So sine theta equals root 3 over 2. So therefore arc sine root 3 over 2 is equal to theta, which will be equal to, calculators out, 60 degrees. So 60 degrees. So what this represents is an anti-clockwise rotation of 60 degrees about the z-axis. It's always an anti-clockwise rotation when talking in matrices. The positive direction is anti-clockwise. So we'll say rotation anti-clockwise by 60 degrees. Okay, question 6. That was a nice question. Let's go question 6. Matthew is finding a formula for the inverse function of r sin x. He writes his steps as follows, blah, blah, blah. In these questions, what I tend to do is solve it myself and then see what he's done wrong. So, because then it makes it easier. So I'm going to let y equal r sin x. Therefore, sin y is equal to x. Therefore, e to the y minus e to the minus y, the exponential form over 2 of sin y, is equal to x. For e to the y minus e to the minus y is equal to 2x. I'm going to multiply both sides by e to the y. That's going to give me e to the 2y minus 1. So I've got rid of the e to the minus y now, and now I'm appearing to get a quadratic, which is really what I want to solve, because I actually know how to solve quadratics. E to the 2y minus 2x times e to the y minus 1 equals 0. And that's a quadratic in terms of e to the y, because e to the 2y is just e to the y squared. So that will give me that, using the quadratic formula, e to the y is equal to negative b, so that's 2x, plus minus the square root of negative 2x squared, so that's 4x squared, minus 4ac, so that's going to be plus 4, all over 2. Now I can take a factor of 4 out in here, therefore I can take the 4 outside and make it a 2, because the square root of 4 is 2. And I can now divide by 2. So that will be equal to x plus minus the square root of x squared plus 1. And now I'm going to do that. Y is equal to the natural log, or just log. It's the most useful log, so it's just called log, of... none of that log is just base 10, but the natural log of x plus minus the square root of x squared plus 1. Now you would think you're done here, but you're not, because you have to check with this plus minus. Now ln x can only have positive inputs. The graph of ln x looks like this, so y x, the graph of ln x is like an exponential graph. It goes like this. It doesn't go this side of the axis. So we need to discount any negative solution. Now, this root of x squared will equal x. So the root of x squared plus 1 will be greater than x. So therefore, we can't have this negative solution here, because therefore the x minus the square root of x squared plus 1, no matter what x is, positive or negative, will always be a negative solution. So it's plus. Now, looking at Matthew's proof, I don't really care about the first bit. I care about what he's left it as, and he has left it as r shine x is equal to ln of x plus minus the square root of x squared plus 1. Now, we know the reasoning why we couldn't have the negative solution, so we'll say that ln x can't take negative inputs. And well, that's his proof. So I'm going to write r sinh x should be equal to the natural log of x plus the square root of x squared plus 1. Right, that's part A. Part B is solve ln x plus the square root. See, he even gives it to you in the next part of the question. Square root of x squared plus 1 equals 3. So now that's really r sinh x is equal to 3, and that means that sinh 3 is equal to x. If you type that in your calculator, you will get that that is equal to roughly 10.0 to 3 significant figures. Next question. Question 7. This will be the last question we'll do this video. Find the invariant points. Find two invariant points under the transformation given by 2, 1, 3, 4. And the way we're going to do that is we're going to pre-multiply x and y by that and make sure we get the same value as x and y, the other side. So we're going to get that 2x plus 3y is equal to x. That's just matrix multiplication, so this one multiplies here and this one multiplies here. And x plus 4y is equal to y. And by a little bit of rearranging, we get that 3y is equal to minus x, or that x is equal to minus 3y. And these are basically saying the same thing. So I'm just going to put in 1 to start with. So yeah, let's put in minus 3 for x and 1 for y. And then our other one we can do as, let's say, 9 and minus 3. Thanks for attending this video, and I look forward to seeing you all next time.